students, today we are going to discuss oxides of nitrogen and oxoacids of nitrogen from the chapter P block elements. So first we'll start with oxides of nitrogen. So first oxide that we are going to discuss is dinitrogen oxide or nitrogen 1 oxide, because the oxidation state in this oxide is +1. Okay, and formula for dinitrogen oxide is N2O. Now the common preparation method is like thermal decomposition of ammonium nitrate. So ammonium nitrate, okay, on heating gives out dinitrogen oxide and water. Okay, now what is the physical appearance and its chemical property? So it is a colorless gas and is neutral, and it is unreactive gas. Okay, this is unreactive gas. Now next is nitrogen monoxide or nitrogen 2 oxide. Again, why? Because the oxidation state here is +2, formula is NO. Okay, and it is prepared by reaction of sodium nitrite, ferrous sulfate, okay, sulfuric acid, which gives ferric sulfate, where the oxidation state of iron is 3, and sodium hydrogen sulfate, water, and our product nitric oxide. Now, so it is a colorless gas, okay, and it is neutral, and since it contain odd electron, as we have already discussed the structure, right, of it, Lewis-Duff structure, what we notice is that it contain odd electron, right? So this is paramagnetic in nature, paramagnetic. And this is a reactive gas. Now next is dinitrogen trioxide, okay, nitrogen 2,3 oxide. Why? Again here the oxidation state is +3. Okay, and what is the formula? N2O3. Now what is the preparation? So when nitric oxide and dinitrogen tetroxide is heated, we'll get is dinitrogen trioxide. Okay, now this is your blue solid and this is acidic in nature, okay, and this is unstable in gaseous phase. Now next is nitrogen dioxide or nitrogen 4 oxide, oxidation state +4, and formula is NO2. Now the preparation, so when you do, right, there are number of ways of preparation method. So one which is there in book I am discussing that only. Okay, so when you do the thermal decomposition of this lead nitrate, you will get this nitrogen gas, right, then lead oxide and oxygen, isn't it? Now this is your brown gas, right, and this is acidic in nature, and this is paramagnetic. Again, why? Because this contain odd electron, and but this will get dimerized to give N2O4, right, and this is reactive one, so for that reason it dimerize and give stable N2O4. Now next is dinitrogen tetraoxide, nitrogen oxide 4 oxide, oxidation state again +4, N2O4, which is dimeric form of NO2, right. Now how it form? By simple dimerization of your NO2. Okay, now again this is colorless, either it exists in solid, liquid, it is acidic, right. Now next is your dinitrogen pentaoxide. So formula of it is N2O5. Here the oxidation state is +5, so nitrogen, okay, nitrogen 5 oxide, and it is your colorless solid and it is acidic in nature. So when nitric acid, okay, it is treated with phosphorus pentoxide, it gives phosphoric acid and dinitrogen pentaoxide. Okay, this is a colorless gas. This is acidic in nature and it is unstable one. Okay, and in solid it exists as NO3 minus. In solid state it exists as NO2 plus NO3 minus. And structure for all these oxides we have already discussed. So we are moving to the next topic, that is oxoacids of nitrogen. Nitrogen form numerous oxoacids, but several are unstable in free state and they are known in only aqueous state or as their salt. Okay, some common oxoacids of nitrogen are hyponitrous acid. The formula is H2N2O2 plus 2 oxidation state here of nitrogen. Then nitrooxalic acid, H4N2O4, formula similar to that of oxalic acid, right? And oxidation state here is plus 2. Nitrous acid, so HNO2, oxidation state plus 2. Nitric acid, HNO3, okay, plus 5 oxidation state. And peroxynitric acid, so the formula is HNO4 and it has oxidation state plus 5. So this hyponitrous acid, okay, this is weak acid and it is known as its salt only. So then nitrooxalic acid, so this is highly explosive, okay, difficult to get in pure state. Then nitrous acid, it is weak acid and are unstable, so this is your acid, okay, so and it is very highly unstable. And your peroxo acid, it is unstable and explosive in nature. So out of these oxo acids of nitrogen, okay, so the important one is your nitric acid, which we are going to discuss now. Now first we'll discuss preparation of nitric acid, okay, in small scale or in laboratory. So how we prepare is we just heat, okay, so your nitrogen, sodium nitrate with sulfuric acid, sodium nitrate and sulfuric acid. So we'll get is sodium hydrogen sulfate, okay, and nitric acid. So this is the preparation in small scale. Now in large scale or in commercial scale, okay, so we prepare nitric acid by Ostwald process. Nitric acid, okay, so it is prepared commercially by Ostwald process, right? And in this process, this is the key step, the reactions of ammonia, okay, with oxygen using platinum, okay, as your catalyst. So this is the key step here. So in order to get the better yield, okay, so the reactions is controlled out here by maintaining the optimum pressure and maintaining the optimum temperature. Now, so in this chamber, okay, converter, what happen is the reaction taking place is like ammonia, so it react with oxygen, okay, and form nitric oxide and water. And here the optimum temperature maintained is your like 500 Kelvin and pressure 9 bar. So this is the key step. Now, so nitric oxide, the gas, okay, it is then passed through the oxidation chamber where it will further, okay, get further oxidized to nitrogen dioxide according to the equation. Nitric oxide, which is a gas, right, it will get further oxidized and it give nitrogen dioxide gas. Okay, now this dinitrogen gas will pass to the absorption tower, okay, where it is dissolved with water to give nitric acid. So nitrogen dioxide, water, okay, it will give nitric acid and byproduct is your nitrogen oxide. Okay, now this is again recycled for further oxidation to your nitrogen dioxide and for the preparation of your nitric acid. And here, okay, this aqueous nitric acid, okay, is then distilled up to 68% by mass of your HNO3. So that means, so nitric acid which you are getting from this whole process, okay, so it is only about 68% by mass. Now it is made up to like the water is removed, right, and it is dehydrated up to 98% acid on passing through the sulfuric acid, okay, H2SO4, which act as a your dehydrating agent, and after this, so we'll get about 98%, okay, nitric acid. Again, so what are the different steps in this process? So first, ammonia is oxidized to nitric oxide and water. This nitric oxide will pass to the oxidation chamber, where it will get further oxidized to nitrogen dioxide, and this is then treated with water, okay, dissolved in water to give nitric oxide, and from this, after distillation and all, will get 68% by mass of nitric acid, and this is further dehydrated up to 98% acid with sulfuric acid. Now next is physical properties of nitric acid, okay. So in pure state properties, so physical first, so pure, so they are colorless liquid, freezing point it is about 231.4 Kelvin, boiling point 355.6 Kelvin, and laboratory grade nitric acid, okay, it contain your 68% nitric acid by mass. And in gaseous state, okay, so it will have the planar structure, so HNO3 in gaseous state, it will have the hybridization state sp2, and here H, okay, this is the structure for your nitric acid in gaseous state. In aqueous state, your nitric acid will act as strong oxidizing agent, okay, strong oxidizing agent, it's a strong acid, and in aqueous solution it produces hydronium ion, and for this reason this is acidic in nature, so the highly acidic, highly strong oxidizing agent, okay. And concentrated nitric acid is a strong oxidizing agent and attacks most metal, okay, except noble metals like your gold and platinum. Now the product, okay, of your oxidations by nitric acid depends on your nature of the metal, it depends on the concentration of acid and the temperature. So for example, now, so this is your we know that every time whenever your acid reacts with metal, it gives out hydrogen gas, right? But here we are getting water. Why? Because nitric acid is a very strong oxidizing agent. The hydrogen release will further oxidize, right, reduce this to your oxides, nitrogen oxide and your nitrogen dioxide. So in this case, when your copper, it is reacting with your dilute HNO3 nitric acid, okay, you are getting see, you will get your nitrate, metal nitrate same, but like the reduced form of your nitric acid will be different, okay. So here you are getting a nitric oxide, okay, when you are taking your dilute HNO3, and when you are you're taking, reacting your metal with concentrated one, what you are getting is nitrogen dioxide, okay. You are getting copper nitrate, water, nitric oxide and nitrogen dioxide. That means the product depends on the concentration of the acid. So now when you are taking zinc, which is more electropositive than copper, right, then what is happening when you are reacting with your nitric acid dilute, you are getting dinitrogen oxide, and when you are using concentrated one, you are getting nitrogen dioxide and zinc nitrate along with water. So this is how your nitric acid react with metal, okay. The nature of metal, see, when you change the metal, you are getting different product, right? And it also depends on the concentration of your acid. So now concentrated nitric acid, okay, it attacks some non-metal also, like, so nitric acid will oxidize iodine to iodic acid, okay, then carbon to carbon dioxide, and your sulfur to sulfuric acid, and phosphorus to phosphoric acid. Okay, so again nitric acid is oxidizing iodine to iodic acid HiO3, okay, carbon to carbon dioxide CO2, then sulfur to sulfuric acid H2SO4, and phosphorus to phosphoric acid H3PO4, and the rest product is your nitrogen dioxide and water. So you याद करनो, then remaining concentrated sanga, whenever it is reacting, it will give nitrogen dioxide and water as other byproduct. Now this brown ring test, which is very important, okay, it's important while you doing the qualitative analysis of some inorganic compound. So this is usually, okay, the test for detection of your nitrate ion. Now what we do in this test is like, okay, to the aqueous solution here containing nitrate ion, okay, so it is to it ferrous sulfate solution, freshly prepared ferrous sulfate solution is added, okay. After that, to the mixture, okay, slowly sulfuric acid is added alongside of this test tube, okay. Now what happen is, after some time you will see the brown ring. Now what is the chemistry behind it? So when you are reacting your ferrous sulfate, okay, from ferric ion from ferrous ion from ferrous sulfate, nitrate from your aqueous solution of your salt, okay, and when you add acid, so it give is your nitric oxide, and it oxidize your ferrous to ferric ion, okay. Now this three will again combine, and why you are getting brown ring is like, so the three will combine and form a colored complex, okay. So this is your like penta aqua nitrosyl iron 2. So this brown ring, okay, it is formed at interface between your sulfuric acid, okay, and the your solution, which and this indicate if you are getting brown ring, then it means your nitrate ion is present in the salt. Now last we are going to discuss is the use of nitric acid, okay. So nitric acid is used in manufacture of ammonium nitrate for fertilizers, okay. So it is used to prepare your sulfuric acid by leach chamber process. Now it is also used in manufacture of explosive like TNT, trinitrotoluene, okay, nitroglycerin or picric acid. So it is used in preparation manufacture of dyes, perfume, silks, okay, and nitrate for use in explosive and pyrotechnics. So pickling of stainless steel, it is also used in picking of stainless steel, that is removing the stain or heat tint layer, okay, which is formed during welding, and etching of metal and purification of gold and silver is done, right, by using aquaresia. So what is it? It is your mixture of hydrochloric acid and concentrated, okay, nitric acid in 3:1 ratio. Thank you all.